Hello, it's a crazy math nerd here. I'd like to talk a little bit about how we're going to go to this Riemann sum idea to a definite integral. So this is calculus in motion, and I just want us to conceptually think about a few things. Let's look at the area from A to B if we do left rectangles. Just one. That's not very good at all. There's a whole bunch of the area that's not under the curve. It's somewhere out here. Let me see. Ooh, didn't mean to do that. It's all right here, right? And then I didn't get this, and this is just not very good. But what would happen if I made more rectangles? Look what happens to the error. See how the error gets smaller? And what's over is smaller. What's under is smaller. Look at that. Wow, it's amazing. So the more rectangles, the more divisions I have, the less error I have between the true area and the approximated area. All right, so we're going to stop that. All right, now, it's not stopping. There we go, stop. I'm going to reset it, and, sorry. And then I want to now look at right rectangles. And those are the blue. And notice that there's not a lot of error for them either, right? And it looks like the error that's over here for the left and the error that's over here in the right are kind of countering each other. And then I would like to, hide those. There we go. And I'd like to show the trapezoidal rule. Trap's pretty good right there, isn't it? What if we just had one? What if we just had one? One trap's not good. Okay, so let's do one trapezoid. That's not very good. But again, the more that we do of these, the better we get, right? And that's just the way it goes. So any kind of approximation is better if you do more shapes. Do you agree with that? All right, good job. All right, so now let's go look. Oh, no. Now let's go look at some more. There we go. Let's go look at some more things. So what we really would like to do is we really would like to have as many subdivisions as possible, and we'd like to add up all those areas. And we think that if we could do lots and lots and lots of them, there would not be a lot of difference between the area between the curve and the axis and our approximation. So let's go through and look at this. Here is my favorite curves, just a little squiggly. And each of these are evenly spaced out, and they are spaced out so the width of each rectangle would be b minus a over m. Because the distance would be b minus a, and this is the nth rectangle. So each distance would be b minus a over m. So this little guy right here, let me change my color. I want a different color. This little guy right here, and again, I don't know why I cannot write with this thing. There we go. Here we go. All right, that guy right there would be a plus this distance, whatever it is. I'm going to call that b minus a over n. Okay? This guy would be a plus 2 of those, right? Because there's two distances, a plus the two distances, 2b minus a over n. This guy right here would be 3 of those, right? It'd be a plus 3 of the b minus a over n, if we wanted to find the x value right there. So this x, and we'll call this x of 1. This x of 1 would be a plus the distance of each width of each rectangle. And then this guy, x of 2, would be a plus 2 of those, right? Okay. So if I wanted to talk about the area of these rectangles, now let's just say I'm going to do a right-hand rule. It doesn't really matter because as we saw a minute ago, if you do right or left, the more you do, the better. So we're just going to do a right-hand rule just for fun. So what we're going to do is we're going to find the area of this, of this guy in general, okay? Here we go. We're going to find the area of this guy. So, area of that guy. So what would the area of that be? The area of of rectangle 1, call that rectangle 1, would be the width, which is b minus a over n, times the function's value at whatever the x is. And we said the x is going to be this, so a plus b minus a over n. So that would be the area of the first rectangle. The area of the second rectangle would be b minus a over n, and the function's height at the second x. And we said that second x is going to be just a plus 2 of those. So let's write that a plus 2 b minus a over n. Okay? And then that would be rectangle 2. And then rectangle 3 would be b minus a over n times the function at the third value. And the third x would be a plus 3 of those b minus a over n. I didn't put 3 there. Okay. So I think I see a pattern here. And so what I'd like to do is I'd like to write something that does this symbolically and adds it all up. Okay? So I'm going to do that. I'm going to write a sigma. Because sigma in mathematics, this big Greek S, means to sum up. And so I'm going to add up all of the b minus a over n's. See how that's common in all of them? And I'm going to write the function in terms of a plus b minus a over n times, and this is called a counter, times I. Because every rectangle, see that second rectangle needed 2 distances away from A. The third rectangle needed 3 distances away from A, right? Those common differences. So what I'm going to do is I'm going to say I equals 1 to n. And by me putting the counter on the sigma, that means put 1 in there, plus put 2 in there, plus put 3 in there, plus put 4 in there, all the way till we get to n. And so that will add up all the areas of all the rectangles. But, you know, I kind of need to do that thing where we're doing on the calculus of motion where I'm doing lots of them, right? I want to do lots of rectangles. So what we're going to do is we're going to put a limit on here, and we're going to say the limit as n goes to infinity. Because what would that do? That would make the number of rectangles go to infinity, which means that would be a whole bunch, right? We'd have a lot of them, which means your error would be reduced to nothing. And what would n do to b minus a over n? If n gets really big, that makes the width of each rectangle be very, very small. So when we talk about this, what we're doing is we're adding up infinitely many rectangles, areas of rectangles, with infinitely small widths. See that infinitely small width right there. So we're adding up infinitely many areas of rectangles with infinitely small width. Okay? So let's see how that's going to pan out for us in a problem. So let's say I want to tell you this. I want to write this, but I want to write it in terms of the Riemann sum. So let's write that sum again. The limit as n goes to infinity, and I'm going to add up, right, from 1 to n of, and I'm going to write this backwards. I'm going to write my f first. I normally do that. Of a plus b minus a over n times I. I is just the counter. I know that's very weird, but that's you need to know where to start and where to end in your summation, okay? And then times the b minus a over n. Okay? So we're going to take this guy and write it in terms of Riemann sums. Okay? Here we go. So notice that every Riemann sum has the limit and the summation because we want to have infinitely many of these rectangles, and we want to sum them all up, right? So that will always look the same. And then we got to take the let's do this part first. This is easier for me. So b minus a are actually these numbers on the limits, on the integrand. And so b is 2. So 2 minus negative 1 is 3. And that is the distance between b and a, right? If you go from negative 1 to 3, that's a distance of 3. So instead of writing b minus a over n, we're going to write 3 over n. And that means when I get ready to do this part, to find the y values, so this is your height times your width, right, areas of rectangles. That means I'm going to have to put right here where it says b minus over ni, I'll write 3i over n, okay? Because that's what I know that is. So this says to me, this piece, says you're going to put this, whatever this is, inside of the function. So let's write out what that's going to be. What is a? A is negative 1. So negative 1 plus 3i over n. That is the x of that function. That's like the x of the function, right? F of x, right? Where a is negative 1, b is 2, and b minus a is 3, and then over n, and then that I is just the counter. So this is the x of the function. So you need to put this wherever the x is in the function. So I'm going to do that. That's x cubed, so I'm going to say negative 1 plus 3i over n cubed. And there you go. We have taken a definite integral and written it as a Riemann sum. So these two statements mean the same thing, right? They both mean, I'm going to move this over closer, they both mean to find area between the curve and the axis from negative 1 to 2. Okay? Let's go the other way. So now I see the limit and the sigma. So this is actually the Riemann sum, and I've got to figure out what the definite integral is. So I know that the distance between a and b is 1, see? Because that is b minus a. All right? And where can I find a? It's going to be in the function added to the I thing, added to the counter thing, right? So that is a. Oh, I just wrote a instead of 1. So 1 is a. If b minus a is 1, that means b is 1 away. B would have to be 2. So I got my a by looking what's added to the I thing in the parentheses in the function. And then I said this number over the n is b minus a. So b has to be 1 away, so add 1 to that and you get 2. And then the function is whatever the weird thing is inside of. And so I see 4x squared. So the function is 4x squared, and they have put my a plus b minus a over n inside of that. So I know that's the x, and then dx. Okay, hope that's helped a little bit. Have fun.